Hello friends, this is Sudha, Assistant Professor of Mathematics, Hindustan Institute of Technology, Coimbatore. In this video, let's discuss the role of graphs in discrete mathematics and its applications in engineering field. Introduction to graphs in discrete mathematics. Graphs are powerful tool in discrete mathematics used to model and analyze relationship between objects. Graphs are everywhere, from social networks to computer networks to transportation systems. And graphs help visualize and solve problems involving relationships and connections in these areas. Definitions and terminology. A graph is a mathematical structure consisting of a set of vertices and a set of edges. Simply, we can say it's a collection of vertices connected by edges. Vertex. A vertex in the context of graph theory is a fundamental unit or point in a graph where edges meet. It can represent an object or entity in various applications, such as a person in a social network, a city in a transportation network, or a computer in a computer network. Edge. An edge is a connection between two vertices in a graph that represents a relationship between them. In a graph theory, the degree of a vertex is the number of edges connected to it. There are different types of degrees depending on the nature of the graph. Path. In a graph theory, path is a sequence of vertices connected by edges. It represents a way to travel from one vertex to another in a graph. Types of graphs. Graphs can be classified into various types based on their properties and structures. Here are some common types of graphs. Undirected graph. The connection has no direction, indicating a bidirectional relationship. For example, in a social network like Facebook, users can be represented as vertices and friendships as edges. Directed graph. The connection has a direction indicating one-way direction. For example, a one-way street. Weighted graph. The connection has a weight or cost associated with it, representing the strength or capacity of the relationship. For example, distance between cities. So, obviously, unweighted graph is a graph where all connections are considered equal with no specific weight. Graph representation and data structures. Graphs can be represented in various ways using different data structures. The choice of representation depends on the specific requirement of the application, such as the efficiency of operations like insertion, deletion, and traversal. Here are some common graph representations. First one, adjacency matrix. A matrix where rows and columns represent vertices and entries indicate the presence or absence of an edge. If the graph is unweighted, the matrix can be binary. 1 for presence of an edge, 0 for absence. If the graph is weighted, the matrix can store the weights of the edges. Next is adjacency list. A list where each element represents a vertex and contains a list of its adjacent vertices. For weighted graphs, each entry in the list can be a pair. Incidence matrix. It is another way to represent a graph, particularly useful for certain types of graph algorithms and problems. It is a graph where each row represents vertices and columns represent edges, with entries indicating whether a vertex incident to an edge. Graph traversal algorithms. Graph traversal algorithms are fundamental techniques used to explore nodes and edges of a graph. Two primary graph traversal algorithms are depth first search (DFS) and breadth first search (BFS). These algorithms are essential for solving various graph related problems, such as searching for specific nodes, checking connectivity, finding shortest paths, and more. Depth first search. DFS explores a graph by starting at an initial vertex and exploring as far as possible along each branch before backtracking. This is used in pathfinding, detecting cycles in graphs, and solving puzzles like Sudoku. BFS, breadth first search. BFS explores a graph level by level starting from a chosen vertex. It uses a queue data structure to explore all neighbors of a vertex before moving on to their neighbors. This is used to find shortest path in unweighted graphs and crawling the web, finding all researchable web pages. Graph optimization problems. Graph optimization problems involve finding the best solution according to a specific criterion, such as the shortest path, minimum spanning tree, or maximum flow. Shortest path. Finding the path with the least total weight between two vertices. Minimum spanning tree. Finding a tree that connects all vertices with the minimum total edge weight. Maximum flow. Finding the maximum amount of flow that can be sent from a source to a sink in a network. Let's see some of the applications of graph in computer science engineering. Graphs are versatile structures used in various applications in computer science and engineering. Here are some prominent applications. Network routing. Graphs represent computer networks where nodes are routers and edges are communication links. Network routing is finding the most efficient path for data packets in a network. Social network analysis is an understanding relationships and patterns in social networks. This helps identify influential users, community detection, and spread of information or diseases. Web search. Google's PageRank uses graphs where web pages are nodes and hyperlinks are edges to rank the importance of pages. Recommendation systems. It recommends items by finding users similar to the target user and suggesting products, movies, or other items to users based on their preferences. Real life applications of graphs. Graphs are incredibly versatile and have countless real world applications. Beyond computer science, they are used in various fields, including transportation, logistics, and biology. In transportation systems, graphs are indeed extensively used to model road networks, flight routes, and public transportation systems. Logistics. Graphs are instrumental in logistics for modeling and solving various optimization problems like optimizing delivery routes and warehouse layouts. Biology. Graphs are extensive used in biology, such as representing protein interactions and gene networks. We have come to the conclusion. Graphs are essential tool across various domains in modeling complex relationship and interactions. As technology continues to advance, the applications of graphs are expected to grow even further. Moreover, graphs are used in AI systems for tasks such as knowledge representation and reasoning. Graphs algorithms are being developed for quantum computers. At last, graphs are used to analyze, visualize large data sets. Friends, I hope you have gathered some knowledge about graphs from this video. Thank you.